Alright, so this time what we're doing is solving an integral. This one is an indefinite integral because I have no bounds. If you have bounds, then we have a definite integral and it's computing a number, whether it's area or volume or those types of things. But in this case, the indefinite integral is essentially, we're practicing how to crack the antiderivative. I'm not trying to use the fundamental theorem of calculus to compute anything with it or any of the applications. I just want to know how to take the antiderivative of this function. So I've been throwing an integral. I cooked it up, but pretending I haven't, I look at it and I say, what is this? I definitely see a polynomial over a polynomial, and that happens to be degree 0 over degree 3, so it's proper. So I know it's partial fraction decomposition and it's already proper, however it is not factored. So the last step before I make my guesses for partial fraction decomposition is it must be a proper rational function, and the denominator has to be factored into linear factors or irreducible quadratics. So I'm going to do that first. Luckily it has x in both terms. So when I factor that out, I get exactly that. Now it's factored into a linear factor, x minus 0, and an irreducible quadratic, x squared plus 1. From there, what I want to do is make my guesses, my partial fraction guesses. So what we're going to do is we're going to guess that 1 over x, x squared plus 1 is equal to a over x plus bx plus c over x squared plus 1. So actually we're going to have to sneak in a little bit of linear algebra in here depending on how complicated it gets, but I knew that there was 3 unknowns to solve in 3 equations because the denominator was degree 3, so I know this ahead of time. This is the tip. It was degree 3, so there's going to be a, b, c. There's going to be 3 unknowns I have to find. If it's degree 4, it's a, b, c, d, and so on. So what are we doing with this? Actually, what we're now going to do is, this is always the common denominator, first of all. That's the common denominator you're looking for. I want this common denominator to be here and here because I'm adding fractions. So what's the common denominator? Here, this one is missing x squared plus 1, and this one is missing x. So we're going to do exactly that. This is if and only if 1 over x, x squared plus 1 is equal to a over x times x squared plus 1 over x squared plus 1, my favorite dirty trick, multiplying by 1 in the form of b over b, plus bx plus c over x squared plus 1. This one's missing x. I'm going to do the same dirty trick, multiply by x. So now I have a common denominator. Coincidentally, at this stage, if you haven't seen or understood why, now the left hand side and the right hand side have the same common denominator, so you could multiply both sides by x, x squared plus 1, and get rid of it. So now we're going to focus on the numerator, and this is where we're going to get our 3 equations and 3 unknowns from, by setting these 2 polynomials equal to each other. So let's clean that up. We've got rid of the denominator. Now what we're doing is setting these 2 polynomials equal to each other. I'll actually do it in its gory detail, but basically we're expanding and grouping like terms because we have a's and b's and c's. The other thing that's fairly mean in here, because I have the highest degree is going to be degree 2, this is actually a degree 2 polynomial, and what it's saying is this, and that's where we're going to match the coefficients. We have an x squared term, which is 0 times x squared plus 0 times x plus 1 times x to the 0, and then we're going to match that polynomial to this polynomial. So that polynomial, 0x squared plus 0x plus 1 times x to the 0 is actually equal to, now let's group everything together. This is ax squared plus a plus bx squared plus cx. I've just FOILed everything out. And now I'm going to group like terms. I should probably use a square for the squared terms. And then we'll use a circle for the linear terms, and then we can use a triangle for the constant terms. So I have 3 kinds of terms, so I group those together. What that says is 1 equals a plus b x squared plus cx plus a. And now what I'm doing is, I won't write it out again, but I'm matching this coefficient has to be a 0. This coefficient has to be a 0, which gives us c is 0 immediately, and this coefficient has to be equaling a 1. So what that gives us is 3 equations in the x squared, in the x1, and the x0 terms. Shout out, I learned that from Mark Solomonovich, and it's stuck in my brain ever since. So in the first one I get a plus b has to equal 0. In the second one, I get c has to equal 0. And then the last one, I get a has to equal 1. So it's a fairly sparse linear 3x3 system, but if you really want, or if these are complicated and you've seen this, you can augment the matrix, row reduce, and find the unique solution. But I already have 2 of the values, and this one tells me that b is negative. So this immediately says c is 0, a is 1, and from the first equation, b is negative a, so negative 1. So I'm going to use those immediately to put those back into the partial fraction decomposition and compute the integral. Therefore, 1 over x, x squared plus 1 is equal to a, which was 1 over x, plus b, which was negative 1x, plus 0 over x squared plus 1. Therefore, the integral of 1 over x cubed plus x dx is equal to the integral of 1 over x times x squared plus 1 dx, which is now equal to, by partial fraction decomposition, the integral of 1 over x minus x over x squared plus 1 dx. Now that I have that, basically that is the process of partial fraction decomposition. Now it's ready, and the idea is we're going to either get a power rule, natural logarithms, or arctangents as the antiderivative in this case. In this case we both get, because of the substitution and what stayed, we're going to get natural logarithms in both cases. So once we have this, now how do I actually integrate this? Now that I've split the integral into its 2 integrations. This one should hit a nerve. This one is the natural log of the absolute value of x. This one, I see the function and its derivative up to a constant appearing. So I am going to let w equal, why am I picking w instead of u? Integration by parts uses a u and a dv immediately. So if I have to use substitution, and then it turns out after I have to use integration by parts, I have a u equals u problem. So I try to train for regular substitution, use w or t or z, something other than u and dv. So w is equal to x squared plus 1. Then dw is f prime of x dx, which is 2x dx. All I have is x dx. So I'm going to divide, and 1/2 dw is equal to x dx. Remember, we're liquidating x's. All x's must go. So there should be no x's when I'm left. Also, you don't have to crack all the integral eggs all at once. I already see what this one is, so in my next step is what I do. I write this as the natural log of the absolute value of x minus, and now this one I can use this, write this in there, and I haven't quite cracked the egg. This is minus the integral of 1/2 dw over w. If you want, go slow. This is the natural log of the absolute value of x minus 1/2 the integral of dw over w, which is equal to the natural log of the absolute value of x minus 1/2 the natural log of the absolute value of w plus a constant of integration. And here's another one where I should have done this, but in one of our absolute value videos, I do specifically the absolute value of x squared plus 1, and what is that equal to? Itself, because x squared plus 1 is always positive. So because he's always positive, I can just strip off the bars. Why is that relevant? One more step, I guess. This equals the natural log of the absolute value of x minus 1/2 times the natural log of x squared plus 1 plus c. W was x squared plus 1. Don't press the button yet. What the back of the book likes to do is this, so I'll clean this up and I'll write out what our integral is one more time, and I just can't help myself. There's a couple log laws I could do there. What I'm going to first do is do what we won't mention any names, but certain calculus books really like to, at the end of the book, clean it up with some algebra, and then the student says, I didn't get the same thing, and it's like, yeah, they use log laws and clean it up. So this is probably the answer you got, but this is probably what you'll see in the back of the book. If they're mean, they're hiding the answer with algebra. So this is equal to, first of all, number on the outside becomes exponent on the inside. So this is the natural, and you can deal with the negative with using it as one of the other laws, or treat this as plus a negative exponent. I don't care how you do it. Both of them will do the same thing. As long as you use the laws in the right order, it will happen. So this is the natural log of the absolute value of x. I'm going to keep the minus there and put the exponent on the inside. That's the natural log of the square root of x squared plus 1 plus c. And then subtraction on the outside is division on the inside. So what this becomes is the natural log of the absolute value of x over the square root of x squared plus 1 plus c. And then that's what essentially the silly book likes to do, is write it like this. That's technically the answer, but that's probably not what you got when you calculated. They cleaned that up using log laws.